MIP is the standard communications protocol for all existing and future Lord MicroStrain inertial sensing systems. With MIP, data from a variety of sensors and external sources work easily together, regardless of the speed or sophistication of the data from each source. Its strong error checking, organization, and the tools and support we provide allow current and future systems to integrate seamlessly and reliably. MIP will help make your code future-proof.
Hi, my name is Fritz Martin. I'm a staff engineer here at Lord MicroStrain. I'm here to give you a quick introduction to the MIP packet and the MIP packet protocol. We designed the packet to support a protocol. It's originated as the MicroStrain inertial packet. Now we just call it the MIP packet because it has other applications. Some of the benefits of the MIP packet: it's robust. It has a 2-byte startup packet. It uses a Fletcher checksum. It supports multi-rate data, which means you can pack multiple fields of data in a single packet, and you can do it selectively. It's strongly typed data. I'll get into more detail of that as I get down into the presentation. It's easy parsing. We designed it to be easily parsable by embedded processors. And it's compact. 261 bytes is the maximum size of the packet. This is a compromise between size and ease of handling and predictable buffering on a microcomputer or an embedded computer system. So the structure of the packet is straightforward. If you've used packets before, it's very familiar. You may wonder why we designed another packet, but I'll show you as we go along why we needed to do that. The first 2 bytes are the startup packet. They're hex 7565. They translate into a lowercase u, lowercase e, making it easy to spot the packet if you're looking at a binary stream. It also has 5s in both values, which allow autobotting to pick up on a baud rate. The next byte in the header is the descriptor set byte. This is one of the key features of this packet. It describes what type of data is going to be in the packet. And then a familiar payload length byte. That's the 4th byte in the header of the packet. It's followed by the packet payload, and at the end is the Fletcher checksum. It's very common packet structure. One of the important parts of this packet is the payload. It holds multiple fields. Now I want to show you in this field, the 2 bytes that describe a field are the field length and a field descriptor. The field descriptor is a descriptor that comes from the descriptor set that this packet represents. As we go along, I'll show you what that means in terms of handling your data. As a final point, the Fletcher checksum is fairly strong compared to other checksums. It's nice because it does a very good job with smaller data. Our 261 byte packet is ideal for this, and it's easy to compute on any microcomputing platform. The MIP protocol is what the packet supports, and the protocol depends on the descriptors and the descriptor sets. Descriptor sets divide commands and data into logical categories. I'll show you an example very shortly. Each descriptor set can have 255 descriptors, giving you a lot of room to describe different types of data and commands for a given descriptor set. A packet only contains fields from one descriptor set. That means when you get one packet, you can examine that 3rd byte in the header and find out what type of data is in that packet, and you can route it efficiently to the code in your microprocessor or your embedded system. All commands and data are fully described by the descriptor set plus the descriptor. The descriptor set is 1 byte, the descriptor is 1 byte. Together they make a 16-bit value that fully describes either a command or data. Here's an example of different descriptor sets, and you can see how they fall into different categories. The first set in this example is hex 01, which we call the MIP base command reply set. This is covering the basic functionality of our device. Any MIP device that we have always implements the hex 01 descriptor set command reply set. Next one down is a specialty command reply set, hex 0C. It relates to 3D commands in our 3D motion sensor family. Further down, you'll see at the bottom AHRS data, GPS data, and nav data. Those each have their own descriptor sets because the data in those sets is unique. It can be routed to different parts of your code to do different things depending on what your application is. The descriptor set conventions are the last piece of the MIP protocol. What this does is divide descriptor set values into the lower half and upper half so that you have command and replies that are from 00 to 0x7f, and then you have the data from 0x80 to 0xEF. And then we have a reserved set for system commands at the very top. One of our precepts to the MIP protocol is no variance, data is sacred. And I'm going to read this literally because it's very important. I call it extreme data typing. If you get a descriptor set of hex 80 and a descriptor byte of 04, this means it's a scaled accelerometer vector. The units are Gs. It's an array of 3 single precision IEEE 754 floating point values in big endian byte order. Array order is XYZ in right-handed northeast down coordinate system. Those 2 bytes are sacred. Anytime you get data that has that full descriptor, you know that it's exactly what I just described. No variance. You can't switch the order of the axis. You can't change to a different type of floating point. You cannot use a different scale. You cannot use 1 or 2 floating point instead of 3. You have to do exactly this, and you can guarantee that that data is going to be valid. It turns out to be a very, very powerful concept when you're parsing sophisticated data, especially from an AHRS or an inertial navigation unit. A quick sample of our 3DM GX335 shows that we have 5 different sets of descriptors. We have the base commands, as I described, 3DM commands because this is a 3D motion device, and some system commands that we have to control certain system communications modes, etc. And then it has AHRS data and GPS data, and those are the 2 data sets that this device supports. I want to go quickly over the base command because these are the key to communicating to any MIP device.
Integrated into every MIP device is a very small suite of commands called the base commands. If you implement these commands, you can do basic identification and control on any MIP device that we produce.
It's a ping, it's a basic pause and resume, so you can pause the device from streaming data, have it resume data when you're done. It gets a human readable device description, gets machine readable command and data references,
and gets a simple machine health indicator, a single value that tells you if the device is happy or not.
So in summary, the MIP is both a packet and a protocol. The packet was designed to support the protocol. The packet's 261 bytes maximum, so you can do very good buffering management in your embedded system. It can contain multiple commands or data fields from a single descriptor set in a single packet. That means you can actually bundle commands and multiple pieces of data in a single packet, as long as it fits in the 261 bytes. It is strongly typed data. All MIP devices support base commands, and for the details of any particular device, we provide what we call a Data Communications Protocol, or DCP. You'll hear us talk about the DCP quite a bit, and all our DCPs are available online at our website for all our devices.